the utility of play I in profile S is defined as follows. So first, we look which facilities I and Si, and in S, not in S of the other players. So which facilities are exclusively used by player I? Okay, that set. And for that facilities, the player pays the cost of xy of that set. I remind you that xr means the cost when r players use something. So x1 means the cost when only one player uses those. So for these facilities, player I pays the cost of a single user. Now next, look at all the facilities used by player I by some k not equal to I. We look at all such k's and not used by all the others. So here, what is all by all the others, and that's the C means complementarity. So it's not by all the others. So look at all the facilities where two players, including player I, and so on. Eventually, we look at all the facilities where everyone uses that, and then we have n users. So basically, we look instead of what we did before, we looked at a facility and we looked how much the player pays. That was how we defined the utility. For each facility, what is the total cost that the player pays? Here, that lemma looks at this differently. The lemma looks at all the facilities where the player is the only user. Then at all the facilities where the player is the second user, or not maybe the first, but one of the two. It's not like there is an odd on users. One of the two, and so on. And that's actually what the proof is. Of course, formally it needs to be done inductively. Or maybe it's basically a change of the order of sample. That's not the most formal definition, but that's good enough. You can prove that if you write this down as a sum, you can prove that this sum exactly once looks at each facility. Okay, so that's the lemma, which simply looks differently on the utility of a player. And then we're going to prove that every finite potential game can be expressed as a congestion game. So that's what it means to be isomorphic in colloquial words. So consider a finite potential game, a potential game with finite set of strategies, which is what it means to be finite. I remind you that we assume that the set of players is always finite. Unless I'm saying now we don't, but probably we will always assume the set of players is finite. And the potential, because we assume it's a finite potential game, the potential letter denoted by P. For each player, the set of strategies can be written down as player I, the strategies as AI1, so the first strategy. Of course, the order does not matter here. And AIK. We denote those strategies as SI1 till SIK. And the I in the end is something we should remove. Now, so we have written down all the strategies of each player, AI1 till AIK. Now, let us define Ki as all the numbers from 1 to Ki. Aha, I see. K, the number of strategies of player I, of course, depends on I. So it's K of I. It should be in the superscript. Aha, now I understand. 1 second. So play I case ki strategies, small ki of I. Now it's better. Right? Do you see it? Yes. And k capital K of I is the set of all the numbers from y to k small k of I. And k is simply the Cartesian product. So we simply denote all the strategies by numbers. 1 to k of I. These are numbers, and the set of these numbers is k capital of I. Now we need to express this game and its strategies and all that as a congestion game. So if we need to define a set of facilities. So let us define the following set of facilities. For each player, we look at the vector, which is a binary vector of the length kfi. Now, all those vectors, so the Cartesian product of all those vectors is the set of facilities. So please look again at the formula and then look at the illustration. So a set of facilities is the set of all the epsilon. So first of all, you have the first row you have epsilon 1 in the superscript 1, 2 till k small of 1. In the second row, you have epsilon 2 in the superscript 1, 2 till the k small of 2. And so you go till epsilon n, and of course it should be epsilon n, here should be n. 1 second, I'm going to change this as well. And that's in the superscript, it goes from 1 to k of n. Okay, now it's epsilon n. So for each player I, you have a vector to the length of k of I, and that's a binary vector. Those epsilons are all in 0, 1 set, or either 0, 1. And that is our facility set in the congestion game we are constructing. And for each player, define the strategies. So what are the subsets that the player can choose? The strategies as the following ki strategies. So in the original game, player I had ki strategies. Here it has to have ki strategies. Now the strategies are defined as follows. The elf element in the superscript is the element of, so no, my apologies. SIL is the elf strategy of player I. So the elf strategy of player I are all those elements of M. So it's kind of a matrix with different rows. So the elf strategy has all those elements of M, all those facilities, where epsilon IL is 1. So those are facilities, all those where epsilon IL is 1. And of course, there is no condition on others, and that's okay. So all those facilities are the facilities that as a set, they constitute, they're equal to SIL. Okay. So we have now defined a strategic game, not yet. We have now defined a congestion game besides the cost. Now we have to define the cost, and that's going to be the end of the definition. So let us now define the costs. So for each game, for each player, let us just recapitulate. We have written down the strategies of the player in the original game, and they assume that we denoted that the player has ki strategies, and as before, I should be above, or let me just change it so that you will see it clearly immediately. So for each player, we have written down all the ki strategies of that player. Then we just denoted the set of ki numbers as ki capital of I. We denoted the product. Okay, now then we define the set of facilities as all those matrices of zeros, ones. That's what I showed you in the illustration. And for each player, we define the strategies such that the elf strategy of player I, is all those elements of M, because strategy says to say which elements of M it includes. Strategy is a set of facilities in a congestion game, such that epsilon IL is 1. Now we need to define cost functions, and we do it using the fact that the game is a potential game. We omit the details, so till now we have really gone out over all the proof formally. But from now we simply use the fact that the game is a potential game, and we prove that we can define cost function such that the utilities of the resulting congestion game will indeed be the same as the corresponding utility of the original game. Okay, so that's the part of the proof that we show. And now let us recapitulate those two topics. So we defined potentials, several kinds of potentials. It was generalized ordinal potential, and it was a bit more constrictive. It was ordinal potential, and then weighted potential, and then exact potential, which we call just potential, which is probably the most widely used notion. So that's what you will probably use in other areas of game theory most, if you go hopefully to study working game theory later. Then we used a lot of we looked at a lot of properties like that. If you have a maximum of potential, then it's an equilibrium, and therefore finite games where every function has a maximum has an equilibrium. We looked at that process of improvement, and then we looked at the final improvement property and its relationship with potential. I remind you, we proved that a generalized ordinal potential is equivalent to final improvement property. So having an exact potential is even stronger than finite improvement property. So many examples when you have this potential but not that potential, and we saw more on the tutorial. Then we looked at congestion games, which is a very also important class of games. But while potential is something which we can kind of have in a game, a congestion game is a concrete model of something. It's a very wide class, but it's a model. But then we actually proved that any congestion game has a potential, and any potential game which is finite can be modeled in the sense that is isomorphic to a congestion game. Okay, so that is the recapitulation, and you're welcome to send me your questions.